Dear students, let us continue with floating point arithmetic operations. So in this video, you are going to learn about floating point or one of the important floating point arithmetic operation algorithm. So one algorithm for both addition and subtraction. So you are going to learn the algorithm for addition and subtraction. Okay. So let us proceed with this first algorithm in this video. Okay. So before going to this, let us see. So actually we are trying to add a decimal binary numbers, but I want to add two binary floating point numbers, right? So for easy understanding, for initial concepts I am using this decimal representation, right, for easy understanding. For example, see here I want to add these two numbers, right? So you know that, right? So this is the mantissa. For example, you take this number 0.5372400 into 10 square, take this number in this case. So this is the mantissa, right? So this is the mantissa and this is the exponent. Okay, I told that mantissa is normalized, so it's already normalized, right? So exponent we store in bias form, so right, you know this. Now the point is these two numbers I want to add. Okay, so what I need to do, so if I try to make this exponents equal, right, so that I can add the mantissas, that's it. So how to make these exponents equal? The idea is, one thing is this 2 I can make as -1, right? So or -1 I can make as 2. So let us take the first option. If I want to make the bigger number as smaller number, what I need to do? I need to shift this left. Okay, I need to shift this left and subtract this 3 times, right? So if I do that, what happens? The most significant bits will be, I lose these bits. So I lose 5, 3, 7, I lose this. So that's why if I lose the most significant bits, or in this case not bits, these are digits. So we are talking about decimal, right? So in case of binary, these are bits, right? So if I lose this MSB, there is a lot of accuracy degradation, right? So that's why what we do is, instead of making bigger number smaller, we make smaller number bigger. So how to make smaller number big? I can make this right shift. So what I can do this, I can perform point, right, 0. Okay, so what is the difference here? 3 times, right? -1 0 +1 +2 3. So 0 0 158 into 10 square. Right, now this is a number 0.5372400 into 10 square. So this is called, I made this exponents equal so that what I can directly add the mantissas, right? I can add the mantissas, I mean add or subtract, whatever the problem is, add or subtract the mantissas, and exponent of the result is same as this 2. So exponent is 2, but I can, based on the addition subtraction, I can do this result, I can get this result. So this process of making exponents equal, this is called alignment. Okay, this is called alignment. So first step is we need to align. So in case of addition subtraction algorithm, the first step we are going to do, the important step, this is one of the step we are going to do, is the, it's not first step, like this is one of the step, alignment. How to do alignment? So identify the smaller number, right? So in this case identify the smaller number and right shift that smaller number, right? Right shift the mantissa 3 times, mantissa equal to, now how many times I need to do? The number difference between these two exponents, that many times I need to shift this, right? So in this case 3 is the difference, so 3 times I have shifted, right? So difference I need to find, that many times I need to, first of all I need to identify the smaller number, and for the smaller number of the number which has smaller exponent, then for that that mantissa I need to shift 3 times, so that I can add the exponent 3 times, right? So that I can make these exponents equal. This step is called alignment. Okay, so what is there in alignment? Shift the mantissa right equal to number of times equal to the difference between the exponents, and add the corresponding exponent, so for which we have adjusted the mantissa, right? This is called alignment. Okay, this is one of the step. So another step is overflow. Okay, So generally this overflow is observed in the addition. For example, I told that floating point number is always represented in 0 pointer. So for example 0.152 into 10 square, something like this, right. So for example if I get a 1.152 into 10 square, right, this is not normalized, this is called overflow. Basically why overflow, I should get as 0 point, but I got 1. So this 1 I cannot store, I only have a provision to store this 1.152, I cannot store 1.152, right. So this is considered as a overflow. So to avoid this overflow, what I need to do, I need to convert this into 0.1511, okay, sorry. So yeah, I need to convert 0.1152, right. If I do this, if I shift this right one time, right, if I shift this right one time, what I need to add the exponent, right, 10 cube. So how to avoid overflow, just shift one time right the mantissa and add the exponent by 1. This is what overflow, this is how we handle the overflow, right. So basically overflow occurs only during the sum operation, right. So another thing is handling the underflow. So I may get a result as, see I told that what is normalization after point. So whenever I represent a floating point number, after the point I should have a, this is a normalized, but if I have this 0.0123, this is not normalized, right. If I want to make this normalized, what I need to do, I need to, so basically this unnormalized number, this is called underflow, right. So this condition we get only during the subtraction, right. So what I need to do in this case I need to shift left. So I need to make this as 0.123. So if I shift left, what I need to decrement the exponent by 1, right. So 1 into 10 power 1. So this is called underflow, okay. So underflow, how to handle the underflow, shift left one time and decrement the exponent by 1, right. So shift left the exponent and shift left the mantissa and decrement the exponent by 1. So this is called underflow, right. So why underflow is required, to make the, generally whenever we perform subtraction we may get an underflow. So but this is not a normalized, so we should get a normalized result, right. So for that we need to make this as, convert this. So to convert this 2 times I need to shift left, that is why -2 I need to do. So finally I get 0.35 into 10 power 3. So this is called underflow, okay. Now let us see the hardware for performing the addition and subtraction. So in this case see here, so we have floating point number, for each floating point number I can have a provision 3 registers here. So this register we use in multiplication and division. So for addition and subtraction we use this register, okay. Now this register has 3 things, right. One is AS for storing the sign, this entire thing, okay, this entire thing is the mantissa, okay. So this entire thing is called exponent. So exponent is represented with the small letter, right. So the mantissa is represented with the capital letter and the sign is represented with AS with a subscript of AS, right. So but what is this, I am specially interested in A1, why I am interested in A1 means to handle the underflow. You know this, right, this A1 must be non-zero digit. So to explicitly detect the underflow, so I have represented, I have given a name this MSB bit for A1, MSB bit as A1, just I named this, okay. Now what is this notation? So the entire floating point number is represented as AC. In this the mantissa is represented with capital A, the exponent is represented with small a and the sign is represented with AS. This is a notion or notation, whatever you call notion or notation, right. Similarly another register, for storing another floating point number, we have BR, the entire floating point value, in which capital B is the mantissa, small b is the exponent, right. So capital B is the mantissa and B superscript subscript S, this is the sign, and small b is the exponent, okay. So this is the another provision for storing another floating point number, right. So whenever, right, So we know that for performing addition and subtraction we require parallel adder, you know this parallel adder, right. So and the carry of this parallel adder is stored in A. So what I can do with this parallel adder, right. So this parallel adder I can perform addition and I can have this E, right. Okay, I can have this carry bit, right, E as a carry bit, right. Now similarly for exponents I have another parallel adder, right. So for performing so in this case addition and subtraction I am interested in this comparator for exponents, right. Why I require comparator for exponents? I need to compare the exponents such that I need to identify the smaller exponent and make it as equal, make it equal to the larger exponent, right. So that is the, so also shifting provision is incorporated in this register. I told that we need to shift left and shift right, that shifting whatever the shifting provision that is incorporated in this registers. So I can shift this register left or shift this register right, okay. So accordingly I can adjust the exponent, right. So I so just one thing, if I shift this right, I need to add the exponent, right. Shift this left, mantissa left, subtract the exponent. This is the, that's what I explained, underflow, overflow, alignment, all these things, right. Now so let us so suppose I want to compare these two numbers. How can I compare? So here I have an explicit comparator for comparing A and B, but in this case if I want to compare the mantissas, what I need to do, I can go for the technique, right, based on the carry. I told that if I want to compare A and B, I can do A plus B bar plus 1, right. If I do this A plus B bar plus 1, right, if I get a end carry equal to 0 means A is less than B. If I get a end carry equal to 1 means A is greater than or equal to B. So I can use this technique for comparing this to two numbers, two mantissas, right. So but for comparing these two exponents I can use the same technique. I can use this digital comparator, right. I told the digital comparator is a hardware. So this is a hardware. So it compares the two numbers A and B and tells whether A equal to B or A greater than B or A less than B. So this is about the knowledge about the hardware. So this, there is a one more register called QR. So this register we are going to use in multiplication and division algorithm. Also there in multiplication and division there is a provision, there is a requirement for using this parallel adder. We'll see that, right. We'll see this parallel adder, okay. So this parallel adder can do both A plus B and A plus B bar plus 1, both operations it can do. Similarly this parallel adder, right. So okay, whatever it may be, this is a hardware. Now in this hardware let us see the algorithm. So these are the 4 steps in the addition and subtraction algorithm, okay. So what are the 4 steps? So check for zeros. So why we check for 0? So actually here I want to perform this one floating point number is there in AC, another floating point number is there in the BR. I want to perform either addition or subtraction depending upon the problem. Again this AC may be plus or minus, you know this, right. So again BR may be plus or minus. I can have 8 conditions. Similar, see this mantissa is like a fixed point number, like, right. So this is what, so this is a whole number, right. Again, so right. So this sign plus or minus is there in the AS, this plus or minus is there in the BS, right. Similarly this number mantissa is stored in the A, exponent is stored in the A, mantissa is stored in the B, exponent is stored in the small b. Now that, so check for 0 means for what is the meaning? So first, for example, if I want to do this operation, right. So AC plus BR, right. For example in this case if AC equal to 0, what is the result? Result is nothing but BR. So answer you need to get as BR. No need to proceed with the algorithm, directly I can tell that answer is BR. So so but answer must be stored in the AC, right. So you know, you see here hardware, so answer, final answer must be stored in the AC. So what I do, just I transfer, just I transfer. So in this case answer is BR, but answer must be represented in AC. So Br I will transfer to AC, or if Br equal to 0, what is the answer? Answer is nothing but AC, right? Already AC is there in the AC, so no need to do anything. So this is one thing. Or if AC, I want to do AC minus Br, so what is the thing here? Suppose if Br equal to 0, right? So in this case answer is AC, so already it is there in the AC, no problem. But if AC equal to 0, what is the answer? Answer is minus Br. So what to do? How to do minus Br? So first you transfer Br to AC, also you complement the sign of AC, right? So B to Br to AC, right? So also you complement the sign to get the negative, that's it. So this is what checking for zeros. So why we do this step? So why we do this step means, like if we have any, if I give one input as 0, so just I can stop, I can stop computing and just inform the result to save the time, right? So this is the first step I do. Next step is align the mantisas. So alignment, I told alignment. What is alignment? So in this case I need to compare the two exponents, I need to identify the smaller exponent, right? So for whichever is the smaller exponent, I need to make equal as to the larger exponent, right? How to make equal? So whichever the mantissa corresponding to the smaller exponent, I need to shift right equal to the difference between, how many times? Difference between the exponents, that many times I need to shift right and add the exponent, so that both exponents are equal and mantissa will be aligned, right? So once I align the mantissas, make the exponents equal, so that I can add or subtract the mantissas. So how to add or subtract the mantissas? So you already know the fixed point, similar to fixed point addition subtraction, right? There are 8 cases are there. So I already told that, explained exclusively, I will again tell in this context, right? So right. So similarly, after getting the result, right, I need to ensure the normalized value. Why? So normalized value means I should get 0 point answer, 0 point non-negative number like 0.1 I should get. I should not get answer as 0.0 something, right? I should get this. So in case of addition, there is a chance of overflow, right? So for overflow, what I told, I will get 1 point on something answer. So I need to shift right one time, I need to shift right one time, and so that to make 0.1 and add the exponent. Or in case of subtraction, I may get an underflow. If I get underflow like 0.0, so I need to shift left and subtract the exponent, right? So these are the 4 steps I need to do. Okay. Now let us go for the algorithm, right? So this is the algorithm. Okay. So let me okay. Right. So this is a simple thing, but is given very complicated way. See, first step, what is this first step? Check for zeros, right? So what is meant by check for zeros? So I told that, right, I am doing the operation as AC plus or minus BR, so right, if BR equal to 0, okay, so I want to do either addition or subtraction, okay, I give inputs in one input in AC, another input in BR, start the algorithm, right? So I will first I conditional check I do, if BR equal to 0, directly end the algorithm, right? BR equal to 0, directly end, right? That's it. Why means AC is the result, so already AC is there in the AC. But if BR not equal to 0, then proceed, then go further and check for AC, right? Again, if AC is equal to 0, right? If AC equal to 0, just transfer BR to AC. Why means I need to show the result in the AC, so transfer BR to AC. Now check for the opcode, right? So check for the opcode, if whether you want to perform addition or subtraction. In case of addition, what is the result? Result is AC, right? In case of, but in case of if AC right, if AC equal to 0, the result is, sorry, if AC equal to 0, the result is BR. So the result is BR. So what I need to do? I need to just transfer BR to AC. Already I did that, right? But in case of subtraction, if AC equal to 0, the result is minus BR, right? Now already I transferred the magnitude BR exponent and mantissa to AC. I need to reverse the sign, right? For reversing the sign, what I need to do? AS bar, right, as. Just I need to complement the sign. So this is what handling the zeros, that is what same thing I told, right, handling the zeros, right. Okay. So after handling the zeros, the next step is what, if AR is not equal to 0 and if AC is not equal to 0 and BR is not equal to 0, both are not equal to 0, then proceed with the algorithm, right. నువ్వు రావద్దు నన్ను వెళ్ళిపో, ఎవరు చెప్పారు, సరే పెట్టు మేడం, ఇక్కడే ఉంటాం మేడం, ఓకే ఓకే మేడం, నేను ఇంకా స్టూడెంట్స్ వస్తున్నారేమో అనుకున్నా, మీరున్నారని తెలియదు, ఓకే వస్తా మేడం, వీడియోస్ చేసుకుంటున్నా. So if right, so sorry for this disturbance. So okay, let me continue with this. So first step is we have checked for zeros, right, it's over. Now the next step is align the mantisas, right. So how to align the mantisas, that's what I told, I need to check for the exponents, right. So compare this step stands for comparing the exponents, right, a colon b, I am comparing the exponents. How I compare, I have a comparator for that, right. So comparator will give 3 outputs. What are the 3 outputs? One is a equal to b, a less than b, a greater than b. So 3 outputs it will give. Suppose a less than b, in this case a less than b means what, b is greater. So my intention is to make a equal to b. So how I need to do a equal to b, I need to shift right a and increment the exponent, right. So how many times I need to do, until a equal to b. So that many times I will loop in this and make a equal to b. Suppose a is greater than b, right. Suppose a is greater than b, right. If a is greater than b, what I need to do, I need to shift right b, right. So so in this case a is greater, so I need to make b equal to a. So what I need to do for that, again I need to shift right b. How many times I need to shift right b, such that a will be equal to b. So that many times I will loop. Finally what happens, after few iterations a will be equal to b. Once a equal to b, then I go proceed with the algorithm, right. So in the algorithm what I need to do, just exponents are equal, right. Now I need to add or subtract the mantisas, right. So how to add or subtract the mantisas, see here. So I just check for the opcode, so operation or opcode. So if the operation may be addition or subtraction, right. So in case of addition, what I told, if the signs are equal, I need to do the addition. If signs are not equal, I need to do the subtraction. In case of subtraction, if the signs are not equal, I need to do addition. If the signs are equal, I need to do subtraction. So this one, for detailed explanation, go for the fixed point addition or subtraction. I told this detailed way. So again you can check the signs, just comparing the signs and performing the XOR of the signs and telling whether the signs are equal or not equal. So in case of addition, if signs are equal, in case of subtraction signs are not equal, I need to perform the addition. So what is addition operation? Just for addition, the carry will be there in the E, right. So if E equal to 1, what is the meaning? If E equal to 0, very good, but if E equal to 0, E is not equal to 0, if E equal to 1, what is the meaning? It is not normalized, right. E equal to 1 means what is the meaning? I get the result as 1 point something, right. So E is not normal, so the result is not normal. To make it normalized, what I need to do? I need to shift this one time right, right. So I need to shift this one time right, and after shifting this one time right, how to when I shift the mantissa one time right, I need to add the exponent by 1, right. So I need to shift the one time right. So shifting one time right means what is the meaning? So here you can observe here, I have represented E is there, and this mantissa A, this bit I represented as A1, right. This bit, the MSB bit I represented as A1, right. This is a mantissa. So what I need to do, this E bit should come to A1 bit. So that's what I represented, and this bit should go here, this bit should go here, this shift should happen. So A1 should go here, that shifting I am representing with shift right of A, and E also should come to A1, right. So that shift I am explicitly representing E has come to A1, right. So this is what I represented here, and accordingly adjust the exponent and end the algorithm, that's it, right. But if E equal to 0, no need to normalize, already it is normalized, so just end the result, right. This is in the case of addition, right. Now in case of subtraction, when to do subtraction? In case of addition, if the signs are not equal, do the subtraction. In case of subtraction, if the signs are equal, do the subtraction. So what I told here, in case of subtraction, I need to do a minus b and d. So for that what I do, I need to do either I told what subtraction I'll do. First I do a minus b, right? So if a is greater, I need to do a minus b. If b is greater, I need to do b minus a, right? But whatever it may be, first I don't know whether a is greater or b is greater. So that's why what I do, first I perform a minus b. How I perform a minus b? A plus b bar plus 1. So I get carry, I get the end carry, right? So if end carry may be 0 or end carry may be 1, right? I may get two cases. So if end carry is 0, what is the meaning? A is greater than, sorry, if end carry is 0, A is less than b. If end carry is 1, what is the meaning? A is greater than or equal to b. So in this case what I need to do? I need to do a minus b. In this case what I need to do? I need to do b minus a. So in this case, okay, for example, if e equal to 1, I get a greater than or equal to b, I need to do a minus b. Already I did a minus b, very good, no problem. So again I did a minus b, I may get a possibility of getting 0, right? If a greater than b, very good, a minus b I did. But if a equal to b, the result I may get as 0. So I need to ensure pass to 0. So this is what I told there, right? Here also you can understand this way, right? But if a is less than b, I did a minus b, but I need to do b minus a. How to get b minus a from a minus b? Just take this result is there in the a already. So b minus a result is there in the a. This is what I did, right? Now to get so a minus b result is there in the a, right? To get b minus a, what I need to do? Just take 2's complement of this. How to get 2's complement? A bar plus 1, right? And reverse the sign, right? To reverse the sign, a's complement of a's, that's it. Okay, let me tell you this one more time. What I am telling is, so in case of subtraction, I have 3 cases. What are the 3 cases? So okay, let me look into the 2 cases. So what are 2 cases? What are there? Right? Whether a greater than, if a is greater than b, a is greater than or equal to b, what I need to do? I need to do a minus b. But if a is less than b, what I need to do? I need to do b minus a. This is what I need to do, right? Now, so in this case, if a minus b, what is if a is greater than or equal to b, a minus b, the sign is same as a, no need to change. In this case, b minus a, the sign of the result is nothing but complement of a, right? Complement of a is a bar a, yes. So I need to do this, but I don't know whether a is greater than b or a is less than b, I don't know. So how I identify? For that I do a minus b. Just do a minus b first. How I do this a minus b? A plus b bar plus 1. I do a minus b with 2's complement method, and after doing this I will get an end carry. If end carry equal to 1, I come to conclusion that a greater than or equal to b, right? So if a is greater than b or equal to b, what I need to do? A minus b. I already did that, very good, no need to worry. But if e equal to 0, what I need to do? I need to do b minus a, right? But what I did this a minus b equal to a. This is what I did. Now the result is there in the a. What is there in the a? A minus b. Now I should get b minus a. For that, what to do? I should take the 2's complement. How to get the 2's complement? A bar plus 1. I will get b minus a. Also the sign must be reversed, right? So for reversing the sign, I should reversing the sign is complement the sign. I should do this, right? So this is what subtraction. You can see here, if e equal to 1, very good. What is the meaning? A is greater than or equal to b, right? If a is greater than or equal to b, if a is equal to b, what I need to do? A equal to b, what I get? I get 0, a as 0. So if a as 0, I need to ensure the positive 0. I should not get negative 0. For that, I transfer 0 to AC, right? So 0 to AC, right? So if I get a positive, right? But if, okay, but if not equal to 0, okay, we'll see what to do. This will go this way, right? But equal to 0, I'll ensure that AC must be positive 0, right? But if AC not equal to 0, right? Again I check for, I need to normalize the result, right? I get the result, I get A minus B in the A. Already I did that A minus B in the A, that is there in the A, but I should ensure that this result is normalized. Normalized means, what is the meaning? I should get, so this I told this is a subtraction, right? In the subtraction, what is the possibility? There is a possibility of underflow, right? Underflow. I may get the result as 0.00 something like this, right? 0.00111 something like this. So, but I need to ensure that 0.1, right? I need to normalize this. So, how to normalize this in underflow? Shift left, right? So, if it is not equal to 0, I need to look for this A1. Yeah, A1 again what? A1 is a ASB, MSB bit of A. So, I need to look into this MSB. This MSB is equal to 1, very good, you end the algorithm. But if MSB is not equal to 1, equal to 0, what I need to do? I need to shift left A1, this case, for example this case 001, I need to shift left this until, I need to be in the loop until this A1 equal to 1, right? So, how to shift left? Shift left the A and mantissa and decrement the exponent, right? So, this is what the case of A greater than or equal to B, right? So, if A less than B, what I need to do? I need to do this first, right? What I need to do? I need to complement the A to get B minus A in A. So, already A minus B is there in the A. To get B minus A, I just complement 2's complement of A, I will get B minus A. Also the complement of sign of the result is nothing but sign of B or complement of sign of A. For that AS must be complemented, and do the same step again, do the same step, right? Same step means again in this case also the result may be underflow, may get underflow, right? So, okay. So, let me tell this part one more time. So, what I am doing is, so in case of operation, okay, I may be addition or subtraction, right? In case of addition, if I decide, if I want to do addition, so in case of addition, if the signs are equal, I need to do addition. In case of subtraction, if the signs are not equal, I need to do addition. Similarly, if I decided that I do addition, right? Now I do addition, I get the this result in A, mantissa result in A and the carry in E, right? If E equal to 0, very good, no problem. But E equal to 1, what I need to do? I need to shift right, right? I need to shift right and add the exponent and end the algorithm, right? Now if I decide that I need to do subtraction, so this is the meaning, I will do A minus B, I will do A minus B first. When I do subtraction, if in case of addition signs are not equal, in case of subtraction signs are equal, I need to do subtraction. Once I do the subtraction, right, now I based on the end carry. So, if end carry is 0, A is less than B. In this case the result is B minus A. Also sign is nothing but complement of sign of A, but I did A minus B, I should get B minus A, right? A minus B is there in the A. So, what I do? Just take 2's complement of the result and reverse the sign, complement the sign, right? So, and proceed and complement the sign, the result is there in the A. Now handle the underflow here using this underflow, right? Now the case is that if E equal to 1, the case is A is greater than B, greater than or equal to B. So, if A is 0, the meaning is A equal to B. If A is not equal to 0, it is A greater than B. Again in the A greater than B, there is a possibility that A1 is not equal to 1. So, under A1 equal to 0, so handle the underflow and end the algorithm. Or if A equal to B, ensure that you will not get a negative 0, for that you make AC as 0. AC 0 means what? A is equal to 0, capital A equal to 0 and small a also 0, right? That is the meaning, right? So, all we should make as 0 to get the 0 result and end the algorithm. So, this is what the algorithm regarding the addition or subtraction. So, okay guys, if you have any doubt, please raise, right? Thank you.